Okay, you already know how to expand this. You either write the bracket twice and use foil or the smiley face, or you can use the famous poem, square the first, square the last, twice the product. So there's the product of the first and last, but twice of it. Now, you probably maybe saw as an extension exercise how to handle one of those. Just write it as a squared bracket times itself, and then do your thing on the squared bracket, and then do this great big tentacle type arrangement, get 6 products and then expand. But what would you do if you had to expand something like this? Okay, it'll take far too long to use a slow method. Okay, so there's a method for it. I call it the bricklaying method. Now I'll do it on 2 examples at once. I'll do this example, and I'll also do this example. Okay, now you imagine like you're building a brick wall, layer by layer. Okay, the first layer is to lay down that many plus signs right across the page. I'll just zoom out. Okay, so that's 4 plus signs, and for this one I'm going to have 5. Okay, so that's the first layer of bricks. Now, that's created some spaces. Head up those spaces with capital C's. I'll explain what they mean in a second. Now, third layer of bricks. Go and write that number on the top left of all the C's. Okay, now either count down from that number or up to that number, and write this count underneath the C's to the right. So this is me counting down. It doesn't matter which way you do it. And this is me counting up. Don't forget to include 0. And for goodness sake, check that you don't exceed the number that was at the top. Okay. Now what you do is you go and write this expression. If it's more than one character in brackets, loads of times. That's your, I think, 4th layer of bricks. And now do the same with that. Okay, now this is actually -3 characters. Basically the template we're working on is this. So in other words, if I say what's playing the role of n, it's 5. What's playing the role of a squared. What's playing the role of b, -3b, because you can always imagine that as not as a minus, but rather as the addition of a negative. So the thing that I have to write lots of times is this. This is where you start to regret not having left enough space. Okay, now what you do is depending on the instructions, so if it says increasing powers of A or whatever, then you obviously have to follow that. But you now, on each of these expressions, you do a count down and a count up. So if I was asked for decreasing powers of A, I would do a countdown on the A business. These are powers now. And you must do one counting down and one counting up. So here I'll imagine that I was asked for increasing powers of A, so I'll do a count up on the A's. And so I did a count down there, I now need to do a count up. Always just check that this plus this equals this. And because I did a count up there, I'm going to do a count down. One must count down and one must count up. Okay, now this is where your algebra skills come to the fore, because you need to do a pretty heavy duty simplification exercise. Okay, so what does that involve for us? Okay, so first I'll tell you how to handle the C's. The first and last C's are always whatever number was at the top. And there's a C button for the calculator. It looks like this. Just check you're using it properly. If you do 6C4, you should always get 6. I think. Yep, you should always get 6. But save yourself the time. Do not use the C button for the first and the last, because they're always whatever number was in the power position. Oh, sorry, they're always ones. First and last are always ones. The second and the second last are always whatever number was in the power position. And that comes off a calculator, that's 6. These come off a calculator, that'll be 10. And now the rest of it is just simplification. So it's 16a to the power 4 times 1. 8a to the power 3. 4a squared, b squared over 9. 2a, b cubed over 27. That's a 1. And then b to the power 4 over 81. This one down here, that's a 1. That's a negative 243b5. That's an a squared. That's a positive 81b to the power 4. That's an a to the power 4. That is a negative 27b cubed. That's an a to the power of 6. That's a positive 9b squared. That's an a to the power of 8. And that's a negative 3b. That's a to the power of 10. And that's a 1. Okay? Now, for ones which have a minus, you'll get into the habit of realizing that the expressions alternate in their powers. So this is my final simplification. So see how I'm switching from positive to negative, positive to negative. And there we're done, they're the expansions. Now I know that was time consuming and horrible, but it's a hell of a lot better than any other method for expanding these. Now just check always that you've done what's required. If they say it needs to be decreasing powers of A, then this is sweet. Increasing powers of B says the same thing. Whichever one decreases, the other one must increase. Sometimes they don't get you to do the whole thing. Even if they, so say for example, they might give you a 20 there, and thank goodness give you permission not to write out the whole thing. In that case, I would definitely write out however many they want at the start, but also do it, dot, and then write 2 at the end, just to make sure you're getting yourself properly in the groove. Okay, so I'm now going to explain to you some loose ends. Okay, so first loose end. Sometimes they don't actually tell you all the numbers you need, therefore you need this formula. Okay, so NCR, which I've told you can be done on a calculator, can also be done by this formula here. It's now this is a pretty rubbish formula, but it's the best that I can do. I'll give you an example to help you understand what I'm talking about. Basically, if you were doing NC5, you would go 5 exclamation mark at the bottom, and you would do n minus 1, n minus 2, n minus 3, n minus 4 at the top. Okay, so in other words, keep going until you've got 5 things multiplying by each other. Okay. Now, what is 5 with an exclamation mark? It just means 5 times 4 times 3 times 2 times 1. So if I gave you this, it would be 2 times 1 at the bottom, and then n times n minus 1 at the top. Okay. Now, if I gave you one like this, there's not a lot you can do. You got to go n times n minus 1 times n minus 2, etc., etc., etc. And if you kept on going down there, I'm going to tell you in a second what you would finish at. But at the bottom, you need to go n minus 1, n minus 2, n minus 3, etc. So in fact, I don't need to tell you what you would finish at, because you can just imagine all these cancelling. Okay, so NC n minus 1 is definitely just n. Okay, so that's your first loose end. You've got to know how to handle this business if you don't actually have the numbers. Okay, I'll just give you one final numerical example. 5C3 is 3 times 2 times 1 on the bottom. That's from this. And then 5 times 4 times 3 at the top. Why did I stop there? You stop whenever you've written that many things. Okay? And then you can just work that out. So that's your first loose end. Second loose end is sometimes they ask you to do things like this. Well, that's pretty simple. You just write your answer to the first expression, which I'll just tell you is this. And then you do the most great big tentacle situation ever. Whoops. And sometimes, thank goodness, you only have to think it rather than write the whole damn thing, because sometimes, as a favour to you, they just ask you for a particular term. That's our third loose end. often they ask for the term independent of x. Okay, that just means the term that doesn't have any algebra in it. So I'm pretty sure that in this great big tentacle situation here, the term that would be independent of x would just be from a single source, namely that times that, so that would be 1. Okay, so you need to know what that expression means. And your fourth, because we haven't actually done the method, we've only written down 4 of the terms. Okay, so if you want to use an equal sign, you can write an equal sign there and write a plus dot dot dot. Okay, or if they really do want you to leave all the remaining terms off and just have 4, then I suppose you could write a not equal to sign. Okay, but another alternative is to write an approximately equal to sign. Okay, now you should take issue with that. You should say, surely leaving this term off would make a massive difference. Surely x to the power 4 is a massive number. And I agree, if x was 10, it will be a massive number. But if x is little, it's the complete opposite. If x is little, so for example 0.1, that will be absolutely tiny. So you can use a little approximately equal to symbol there, because the impact from leaving just one term off the end will be minimal. Now, that's all a bit of a side discussion, because your real task is to approximate this. Well, all you do is you just think, if my algebra example became my number example, what would x need to be? I think it would be okay, your fourth loose end is to use this business for approximations. Now I'll just start indirectly on this. I'll give you an example. Let's say you're doing x plus x plus 1 to the power of 4. If you're doing it correctly, you have to write this. If you just randomly left that off, it would in ordinary circumstances be wrong. If they tell you to leave it off, so they say do increasing powers of x, and they say only 4 terms, then you have to write something true. You can't write this, because it's just wrong. You're doing what they instructed, but you're not writing the expansion of this, you're writing the expansion of something else. There's 2 solutions, so that is wrong. One solution is just to write dot dots. Okay, then you've certainly obeyed the instruction, you've only written 4 terms. Another solution is to write a not equal to sign, but that should strike you as a bit strange and going against the grain of maths in general. But here's your third option, and it's this option is, or your fourth option, your third correct one. This is the option they want you to do if you see the word approximation in the question. They want you to write this. They want you to use an approximately equal to sign, and it's your job to check that that is legitimate. Okay? Oh, sorry, that should be an x to the power of 4. Because if the correct answer has an x to the power of 4 there, and your instruction obeying answer doesn't, you might say, surely that makes a pretty big difference. So for example, if x was 10, then leaving that term off would make a difference of 10,000 to the answer. So surely you can't use an approximately equal to sign there. Well, the point is sometimes you can. If x is tiny, so like 0.2 or 0.1 or anything like that, then this will be tiny, because it'll be 0.1 times 0.1 times 0.1 times 0.1. And therefore you can leave it off, because it will make hardly any difference, and therefore when you leave it off you can use an approximately equal to sign. So that's part A. Okay, that's just the algebra part. B is when they give you a specific job. Okay. Well, all you have to do is compare your number example to the algebra example you've just done, and say what's playing the role of the 1, clearly a 1, and what's playing the role of your x, an 0.1, and so therefore you can say 0.1 plus 1 to the power of 4 is approximately equal to 1 plus 4 times 0.1 plus 4 times 0.01 plus 4 times 0.01 cubed. Okay, and that will be the correct answer which you can type, and that will be the approximate answer which you can also type. Okay, so just convince yourself. All I've done is copy out this, but instead of the x's, I've written what was playing the role of x, because in the concrete example we've been asked about, you still have the 1 there, but the x has become an 0.1. So that's your fourth and final loose end.